Hello everyone. We want to build a computer that is more useful than in previous tutorial. As you remember, we have seen how to build a computer that shows that it works. That's all that it could do. We saw at the light emitting diodes number AB hexadecimal, and that was indication that it worked. In the memory chip we had 5 bytes of data, and if you see the second one, that's AB in hexadecimal representation. In binary form, that would look like, put here AB, AB, and in binary form we see how it looks like. It looks like 1010 1011, and that was in the previous tutorial. We saw this, and all these bytes, 5 bytes, were in this memory chip, and the CPU read them one by one and executed them like instructions. And we saw at the light emitting diodes this number AB that we saw before. So now we want, if you didn't watch this last tutorial, you can watch it at the same channel, my channel. But now we are going to build something more useful. We have the same part here. That's CPU read-only memory clock button we don't need. And that's the same computer like in previous tutorial, only this memory chip, it's programmed differently. It's not the content of the memory chip. Before it was 5 bytes only, and it was a program for him to send to the output bus, data bus, byte AB, and we saw this byte on the flip-flop. I'm not going to talk about this first part. You can watch it in the video, but now here we have something else that tells to the CPU to send not only 1 byte of data but few, and also it has when the CPU sends all these few bytes of data, then the CPU going to wait until the keyboard gets pressed, and then the CPU reacts to it by sending another group of bytes of data depending on the key that user presses on the keyboard. That we will see. Now I'll put this back. And as you remember, we had the flip-flop here, but now we have a controller. That's input-output controller. It's like driver for the input-output devices. And we have 3 devices attached to it. The first one is the speaker. He has only one wire, data wire. It's only one wire and ground. And we have also a keyboard, such when we press keys, this controller mini KB, it's just the same chip like this and like that one, but it's programmed differently. These all programs I will include in folder where you can find this video, and all this stuff is going to be there. So this when user press here, this gets to know about this and sends to the input-output controller the key of the pressed keyboard. The keys are programmed here, and this key goes turned to the interrupt byte for the CPU, and this one interrupts the CPU. Whatever CPU does, it interrupts him and tells him to, and the CPU jumps to the place in memory depending on this address that he sends him with interrupt signal on the data bus that we will see. And then the loop, the program repeats only from different block of memory, starts the same procedure but with different data. And what it's going to do, this is the little controller, the same like here, same like here, just this is programmed for working with this monitor, and we'll see that, and we'll see how it works. Disconnect it here for a little while. Now we put the power here, that's 3.7 volts. We'll connect our computer, hold picture like this. That's computer, that's input-output controller, that's input-output devices. 1, 2 with his interpreter with controller, and 3 with his interpreter controller. And these chips are the same, just program is different content. And this, like you see here, 4 pins, they are for programming these ones. You will see in the internet, in the Google, how to program them, but we will see required steps here. So we give voltage to this one, and we hear this speaker said something, and we see here something ready, and these 2 beeps, then what you heard here, and these letters on the screen, they are these very bytes, that the group of bytes that was sent the same way like before. In the first tutorial we saw that like the number AB was sent here in the data bus. Now here went a few bytes of data there and there. They went, and they were understandable for the controller. We taught him to understand, to differentiate these bytes and to sort them out, which is supposed to go here, which is supposed to go there. Now we have keyboard. We press a key. You see the CPU was in waiting state and he was in waiting state, and they waited for the key to be pressed, and when key was pressed, then key code went here, and from here went a signal to interrupt the CPU. That's interrupt pin that we didn't touch in the previous tutorial. This pin is used for the CPU to pull when for him that it draws it low. Then the CPU understands that it's need to be interrupted, and it reads from the data bus from here byte of data where to jump in memory. That's the second part of the address. The first part is hard coded here, that's 0, and the second part is depends on the key pressed. The controller gives to the CPU jumps in the memory block and reads the song, the bytes of data to be sent here, depending on the pressed key. If we press here, that's the name, I don't know, and here or here, so you see that this code here is more complex. Like before, in previous tutorial we had only 1 byte to indicate that this computer works. Now we have groups of bytes of data, and then we have 10 songs encoded here the same way like the first one that was just 2 beeps. And now we have for each key its own code, its own data that's sitting here at different blocks, at different places here, different addresses. So but the interesting part is, you see, this is computer, this is input-output controller. It's like a driver, the driver for the output devices, for the input-output devices. This input device, this output devices. And if we take them out, these are the main components. These two. This is a computer, this is input-output controller that controls these devices. And now we want to swap the devices. We want to, if it was mini, we want real. This was mini, we want real. This goes away. I'm talking about swapping against this one, against the computer, real computer. That's Pavilion. It's HP Pavilion DV 6000. That can be any computer. Just I had some experience, just I chose this one, and also I have this one. It's now assembled all together, and this the same this is the Amilo LA 1703. And what we're gonna do with them, if we see here, we had input device keyboard, output device LCD with their controllers, and we had speaker. So we have GPU here that controls him. We have keyboard controller that controls the keyboard that's going to be attached here. And for the GPU, we have a converter which outputs LVDS signal here. That's it could do LVDS itself, but I didn't want it to. This LVDS runs on pretty high frequency. That's over 200 megahertz, and I assigned this job to this controller to prepare this signal, to cook this signal, and I gave to it required components: horizontal sync, vertical sync, that's the pixel channel drawing, RGB, that's device enabled, it needs this signal, clock, ground, and plus. The clock runs from here on 68 megahertz. It's capable, it's okay for him, but over 200 it can do that, but let it make it. And we have also VGA. That's VGA port. You can connect a monitor directly here, VGA. That's resolution 800 to 600 pixels, and it goes directly to here. That's VGA signal, and it's easier to make VGA, and it makes it itself. That's frequency 40 megahertz, and we have two crystals here. This is FPGA. If we had controllers, these are all X mega at AX mega, but this one is FPGA, and that's differently programmed, and I have this code for him, the same root folder with this video, and for them too codes. It's a little bit hard to program, and it's a lower level programming level here, but it's much more powerful than them because it handles higher frequencies. Here runs all the time this loop. In loop, this drawing all the time goes on high frequency, and we have keyboard controller. This is just the same board, almost like this. This handles controller handles this keypad with 16 buttons, and on the laptop keyboard we have more than 100 buttons, but it's just the bigger array in memory required here, but nothing more. And here goes adapter. It's connected to pins, and to this adapter we connect keyboard, and logic, all the code almost identical to that one, and you can see in the folder. I'm going to leave there, and we have a speaker, and its speaker is here. It goes the same speaker like here, and the same one wire like here, data wire and ground. and and that's it. Then we have power. It's with batteries. This power part. Uh, this gives us this regulator. I think I will have a look here. That's number one. We'll take number two. 3D model. And so that's this laptop here. And so you see here power part. Here comes 12 volts, 12.6. Here we can disconnect, and we'll put here 12.6, 12.6, and we give it to the laptop. And if you look at here we have 0.14 amperes, and that's because the batteries, they're charging at the moment. And these are the batteries, 18650. These are the same batteries that usually used. Well, nowadays they used these different batteries, but it's very. And this age, laptops of this age, they used all this. Well, many of them used this type of battery, but it doesn't matter which type of battery. I will put this model there in the in the folder, and that's so 12 volts comes here, 12.6, and from here this regulator, it pulls this voltage, converts them, drops them down to 3.7. Input is 12.6, output is 3.7, and that's the regulator. Takes 12.6, gives 3.7. The same like we saw here was needed. And this 3.7 goes everywhere, here, where we have this power label, power, and here too, all this red and blue pins, they mean that this voltage goes here. And we have also this voltage, 12 volts that we give there, goes to the batteries, and one to the battery plus and minus through the BMS, that's battery management system. That's a little board which controls the charge on the batteries. It can charge them if needed. We will see in the required components. These are the batteries, 18650, this type. And this is the BMS, like this, looks like this. And now It's BMS. And it's BMS, and that's this regulator which gives 3.7 volts. It's this regulator. Gets 12 and gives out 3.7. And now we see 11. It was 13 or 14, and now 11. The charge almost complete charging, and we actually don't need this because these batteries are charged almost. And so what we will do, we'll take this what we had here, this computer and input output controller as driver for these input output devices, input device, output devices, and we'll just swap the devices. We'll take the GPU, the same ports, the same cables, the same codes. Here, the same program, the same hardware, all the same. Only devices are different, and their interpreters. Like this, we had interpreter here, controllers, and it's keyboard here, but all these pins at the same place, and we have power and clock, and also we have graphics. This speaker goes here, and we need the power that goes here, 3.7 volts. This, and now why we don't have this beep? Because we have this button, and this button is not active. This regulator doesn't get nothing at the moment. We'll need to push this button then, but the battery is now charging. They connected before this button, and if we press the button, now we don't have input voltage, it's disconnected, but we have batteries that will supply us 12.6 volts, same like wire, but from batteries. And the regulator, it doesn't matter if battery is supplying voltage or directly goes voltage from the wall, from the adapter. The main point is that we have voltage, and on the output we have 3.7. If we switched on, we heard the beep, and we see ready. GPU works. Converter converts to LVDS signal here. Keyboard will check. This speaker works. All the same. Only this device is different. and we want to check this keyboard. That's this laptop keyboard from this DV6000. You need to be careful because it's metal. It's made of metal. And, try press here. I don't see nothing here in the screen. We'll make reset. Something's wrong here. Ah, it came. I'll put this switched off and connect. Yeah, now should work. Now, see, this okay, this okay, this is okay. Should work, yeah. Put it to work. I think I have a bad contact there. Sometimes it disappears the connection, but it doesn't matter. We'll see. yeah, this problem sometimes works, sometimes doesn't. I'll take reset. Yeah. No, everything like you see works, except for maybe we have some connection, faulty connection there, but it doesn't. We have another laptop that is built with better quality. It's the same, absolutely the same everywhere, everything. I have in this I can say that this hardware here in this laptop and here, all the GPU converters and all the rest is just the same. The screens are absolutely the same, hardware is the same, codes, these programs all the same. and memory chip content is the same, only key codes a little bit different, and that's all in this uh, that's all reflected in the keyboard programmer. And here, if we put it, so we have array for the keys, and these are the numbers that the controller, this one or this one, doesn't matter, it's all the same, sends to the out to the input output controller. This one sends there the code from here depending on the key pressed, and this stuff listens to the keyboard. It all the time scans the keyboard, and it's written for the Atmel devices. That's Atmel Studio that you can download, and all the stuff, all these all the written the same way in the Atmel Studio, and you can program them, and all the code on the projects are here for every device. Every project, every solution is here. With GPU, it's a little bit different. It's not Atmel controller, it's FPGA, and the code is different. I've put here a README file that you can check, and here we have this, I don't remember how it's named, this language. This is a hardware description language. That's HDL something, might be. And I have some comments here. That's two protocols, VGA and LVDS, but it's not really LVDS, it's just components for LVDS that goes here at the clock 68 megahertz, and this one makes it faster and prepares real LVDS for the display. And like I said, maybe, I don't remember, if you buy this board, then you'll need to replace clocks. Here we have clock 50 megahertz as a rule. We don't need that. We will take that away. We will put instead of it 40 megahertz. That's for the VGA part. And for the LVDS part, it's at the bottom. I have put 68 megahertz clock. It's in that case, it's adjustable clock by resistors, by a few components. Well, all these models I will put here. I will make yeah, that's the clock for 40 megahertz. That's for the 68 megahertz. It's adjustable. Here we need to put resistor and capacitor with correct voltages. You'll need to see the manual for the if you want this one, that's LTC 6905. You need to see how to make it run on 68 megahertz. That's required for the LVDS. This monitor takes 68 megahertz, but different way. That's LVDS is pretty weird stuff, and you will see if you research about it. I didn't find in AliExpress or eBay, I didn't find such anymore, but I found something similar. But they are needed to be looked at carefully. Everyone needs its own way to program. Here it has, I see, COM interface, and that will need a USB blaster. I think it will come together with this one. In my case, I had already USB blaster integrated to program this one. So also we need a laptop, we need this one for the battery part, controller or regulator, this one, battery management system, FPC. So this one is converter for the keyboard. Keyboard comes here using this one. All these models I will put here, and also we have LVDS converter and boards. For that we need also LVDS converter sits on the deep SOP deep converter, and that's on the board similar that we used already. That's for the controller, Atmega controller. Same. Since these chips they are not standard, they are with small legs, and these legs are too many, and they don't fit in this regular deep. They are not deep packages. So we need a converter. We'll put here this chip using solder wires. You need to be careful how to solder them to avoid joining these legs with each other. Use to avoid this, I recommend using flux, much flux, yeah, and good flux. So this is for LVDS converter, such board. It's adapter. The boards that we saw already in the part 1. Additional boards. So that's it, and we're going to see now how all this stuff works. And for that we are not going to cover any more laptop part. It's, as you see, it's all the same, absolutely the same. Just graphics part needs this one, and this is a little bit different than Atmega, because Atmega is not powerful enough for him. He needs too much care. And so these are output devices altogether, and this part is universal. Now we will connect back these devices. We'll connect the speaker. We'll connect the keyboard. We'll connect the graphics, clock plus ground, and data. And we'll connect the power. And we definitely don't want here 12 volts. .7. You need to be careful about voltage, because very easily these ones can be burned out, and they are not very cheap, about €6. I don't remember exactly, but if you burn them out few times, then you will see that it's not so cheap. .7. It eats 0.11 amperes. Ready? Okay. Now we'll see how it works. Voltage comes here. This one starts to tick. The CPU, about this one you can watch tutorial number 1. And this one wakes up as it starts to tick. It's heartbeat for him. This one wakes up and starts to read the content of the read-only memory. And then it understands that it's supposed to send some bytes of data according to the program here. This what CPU sends some bytes of data here, and the port, output port, here this 8 bits, it sends them here to him, and when he receives the marker 4 bytes AA, that means for him that this the end of transmission. Then the CPU goes to sleep to listen to interrupts from the keyboard, from him, after keyboard pressed. And this one, as soon as he received all the required data and marker end of data AA, then it holds this data. It's been collecting them to the memory, to his memory, and now he's going to read them and analyze this data, and he reads them byte by byte, and every byte he watches what type of byte it is by looking at specific bit. It determines if this is the byte for him or this is the byte for him, and also it sends to them their parts. As soon as it decoded this data, it sends to them, and all the time it listens to this one. As you see, if we start playing something and we now press something else, then it's not going to wait till the music is over. It's just interrupted with new song, and all the time it listens to the keyboard while sending data, while translating data, while listening to the CPU. Well, when it listens to CPU, I don't remember exactly if it listens to the keyboard at the same time, but it's not important because maybe it listens to the CPU for a very short time. The CPU is pretty fast. Now we will see how all works at the byte level. So the CPU woke up, it reads from the memory its content. If you remember, at the previous tutorial we had only 5 bytes of data at the read-only memory. We'll look at them again. On this, and the second byte was AB. That's the byte that was supposed to be sent. It goes to register A. These two rows direct the CPU to put this AB to the register A. Then next byte number 3, this byte address number 2, send content of the register A, by now it is AB, to the port 56. And this port number doesn't mean anything for us, but the content goes here. And at the previous tutorial, and the next one is halt, stop. And in the previous tutorial we saw we connected here flip-flop and light emitting diodes that showed us this byte AB, as you remember, and that showed that the CPU understood the read-only memory program and sent correctly and the byte, and that was indication that the computer works. And now we have a different program. We had this program 5 bytes only in the part 1, stage 1, and now in the stage number 2 we have very many bytes of data, and we cannot understand them. There are too many to understand, to easily read. That's why I put here assembler version that's written in the assembler, by the way, and then converted to the machine codes. And the assembler is not so easy to read also. That's why I made a diagram, this structure of this code, of the content of the memory, read-only memory, and it consists of 6 parts. And the first, what the processor must do, it must jump to sung 0 pointer, and that's just a conditional name. That sung 0 pointer is here. That's after the CPU jumps here, it starts to read from here. That's a place in memory, sung 0 pointer. That has behind this name, it has an address, but I don't know this address. It doesn't matter. It's already defined by the assembler. We don't need this one now, but it's in the code if you're interested. But now we'll see what the CPU must do when he arrives to this place. He must load to the register BC address of sang0, and address of sang0 is something that's behind this name sang0, and we have sang0, sang1, sang2, sang3, and so on, 10 or 9 pieces. And the same way here, sang0 pointer, sang1 pointer, sang2 pointer, and so on. And now to the register BC, the CPU must read address of sang0. Okay, it reads straight away address of sang0. That's this pointer to this byte. That's the beginning of this block, sang0. So this byte's address goes to the register BC. Next, load to register D length of sang0. That's the sang0. It has length 1, 2, 3, 4, 5, 6, 7, and so on. And this all together, sang0 bytes, they represent, they are of some length. And this length, I didn't want the CPU to calculate it for each sang. I calculated it myself, and I just put here fixed numbers. Some number goes here that indicates the number of bytes in the sang0, and it goes to the register D. So BC has a reference to this start of sang0, and D has length of this of sang0, and then the CPU jumps to spit out, and the spit out sits here, and it is the CPU. What it does next, it loads to the register A byte sitting by address at BC. As you remember, in BC we have address of first byte of sang0, that's of him, and the content load to the register A byte sitting by BC, and that's this byte. So this 02 goes to register A, and next output register A to port, doesn't matter what address of port, but matters that A contains now byte 2, and it sends this byte 2 to the port CPU, reads from here instructions, and the last instruction was send 2 to the port. That's the port, 8 bits, and here goes 2, this one. And next, increment BC. That's BC is address of this one, and now it is address on this one, and so on. Increment BC, and decrement D. D is length of sang0. It goes down. If it was, for example, 56 bytes, now it's 55, then 54, 53, and so on with each loop. And increment BC, decrement D, and if D is still bigger than 0, if we have something to read here, then repeat, spit out, go back here. And all the time, all this loop is done is being done. All these bytes are one by one sent here to him until it counter D reaches 0. When it reaches 0, then goes send 4 times AA. That's the marker. That's 4 times AA. That means for him the end of transmission. That the CPU is not going to send anything else from sang 0 after pressing some button on the keyboard. We haven't reached yet to the keyboard. We are going to cover this a little bit later. Send for time AA, that's the marker of end of transmission for him. And activate interrupt mode 2. That interrupt mode 2 for him, that means that it's going to listen to the interrupt. Here's the one interrupt pin, it's connected to here, and this one pulls this pin when you press the power button, or when you press the key here. It sends the interrupt to the CPU using this pin, and CPU knows that it's the interrupt mode 2, like instructed here, mode 2, and that means that on the data bus is present the second part of address where to jump, where CPU must jump in the read-only memory to read next instruction. The CPU was sleeping, now it's woke up by the interrupt from him, and the CPU straight away looks here at the data bus, and it finds here the byte depending on the key pressed, and CPU, and these bytes sends the CPU to specific place in read-only memory depending on the song or depending on the key pressed. That's the interrupt mode 2. You can read it in Google. You can find it in Google if you put in search Z80 IM2. That's interrupt mode 2. So that's we have so far sent from the CPU sent sang 0 to the read-only memory. That's just when we pressed when we connected power. We even haven't pressed anything else. That's by default the sang 0. So the CPU read one by one all these sang 0 bytes and sent them, these bytes, and sent them here to the data bus, and it grabbed them one by one all together, and the end of transmission byte marker was 4 AA bytes, like here, 4 AA bytes. That means in the end of transmission, and the CPU then is going to listen interrupt mode 2. That's enabled here, and put 0 into register I. That's the first part of the jump address. The CPU, when it was interrupted, it looks here where to jump, and that's the second part of this jump address in the memory. But the first part is hardwired. That's just a 0. because the address of the read-only memory can be of 2 bytes. It's big memory, and that's why it takes 2 bytes to address it. And we only can give 1 byte here in the data bus from him, indicating the key pressed and where to jump. And the most significant byte is hardwired. And in our case, we just put 0 here to the register I. You can learn about interrupt mode too in Google, then you'll see how it works. Next instruction, enable interrupts. That's all the time we must enable. When interrupt works, when someone presses button, then CPU is interrupted, everything is okay, but the CPU is going to disable interrupt automatically. And we don't need this to happen. We need to enable all the time this interrupt. And then to listen to keyboard. And then the last instruction here, jump to snooze. And that's where the CPU sleeps. The snooze, that's halt, and jump to snooze. Jump to snooze, jump to snooze, jump to snooze, until the interrupt number 2 occurs. Then the CPU jumps depending on the map here. The CPU is sent by the data bus when interrupt occurs. This one interrupts the CPU and puts on the data bus jump address depending on key pressed, and this jump address sends the CPU to grab the second part of address from here. It grabs, and these are the addresses, real addresses in the memory where to jump depending on the byte and the data bus that controller sends here. It's not directly like controller gives the CPU address where to jump to read song. The CPU goes here and fetches from here, from table, already that address, that's correct one to jump here, or whatever song it's selected. You can read about this scheme, about how it's done in the interrupt mode 2, about this Z80 CPU. It's not hard to understand, but it's not just directly this address. These addresses are actually in this table in the memory. But next, what does CPU? It snoozes, it sleeps. And what goes next? Next wakes up the controller when it receives AA, 4 bytes AA as a marker of end of transmission from the CPU. Then it starts to not to listen to CPU, but all the time it listens to keyboard, but the CPU too listens to interrupts. But the controller, as it has collected all the bytes to his memory, it now starts to read, to analyze them byte by byte. If we see how it's programmed, that's the solution. That's Atmel Studio. You can learn about it from Google. And this Atmel Studio is used to program these guys. This one, this one, this one. That's the same chip. the same controller, and those ones, this. So we now see how the content of this one. Now is the main function, that's get data from CPU, that's listening to the keyboard, and get content from the CPU. We'll take a look at that. Get content from the CPU, that it reads to the memory, and here the speaker memory, and it has also LCD memory, and here's the AA byte marker. If it encounters 4 bytes AA, that means for him that's no more byte the CPU is going to send, and it starts to read bytes, speaker bytes, analyze all these bytes, and makes of them 2 arrays, one for the speaker and one for the LCD, and then it's going to send going to start timers that control the speaker and the LCD. But what means this data? If we look at read-only memory once again, at the assembler version, we have these procedures, that's pointer, sung6 pointer, sung7 pointer, sung8 pointer. They are almost the same. There's a hardwire length of sung6, hardwired length of sung5, and so on. There's BC, goes address of sung6, sung8, and here we have a spit out section that we covered. Also here for bytes, AA bytes, that's a decimal representation of AA, and 4 times it's going to be sent to the controller. Interrupt mode 2, that's all the assembler representation of what we saw in the sections in the diagram. And these are songs. These are songs itself, and we see these strange bytes. What does they mean? What do they mean? If we scroll down, meaning of data bytes. Data bytes consist of group 4 byte each. All these bytes, all this stuff divided by 4. Each 4 bytes represent one note or one symbol. For example, R, E, D, E, or note, musical note here. And we see these 4 bytes. These are one group, one note, or one symbol to the graphics. In case it's we'll see next. So these bytes, each group consists of 4 bytes, byte 0, 1, 2, 3. And for the controller, when it analyzes these bytes, byte number 3, byte 3, bit 7, that means for him type of group or type of chunk. And if that's meant for speaker or is that for LCD? If that's an audio byte, audio note or LCD symbol, and that depends what if bit 7 is 1 or bit 7 is 0 of byte 3. Byte 3 bit 0, when high, then it means the last chunk, last byte, last group of song. That's the end of transmission, we can say so. And in case of speaker data, byte 0 and 1, they byte 0 and 1, byte 0 and 1, byte 0 and 1, byte 0 and 1. That's frequency of note in hertz. They represent frequency in hertz. And byte 2, duration of note in seconds. Seconds divided by 10. By 3, that's the seconds divided by 10. Number of seconds divided by 10. But we have only 2 notes at the song 0, dun, as you remember, and word ready. That's default song which plays even if we don't press button on the keyboard. That's then these 2 notes, and then goes graphic, 5 letters ready, and he understands if it is note or if it is graphic by looking at byte number 3 at bit 7. Byte number 3, 0, 1, 2, 3 at bit 7. That's 84, 84, 84. That means bit 7 is 1. And that's for graphic. And if in case of LCD data, if it's 84, that it's LCD, that's bit 7 is 1. Then byte 0, 1, that's color of data. As you see, they are all zeros. Color we don't use for now. And byte 2, that's data itself. That can be ASCII code or code of primitive, pixel, circle, whatever. It's not well implemented, pixel, circle, but the ASCII code, you can put it here. That's 52, 45, 41, and byte 3, bit 1, end of line for ASCII 2 characters. That's like enter key, but we don't use this one. It's not implemented. You can implement it if you want here or here. I don't remember already. Here, but we don't use it. But the ASCII code we need to differentiate between letters, we use it. And byte 3, bit 1, end of line, we don't use it. Byte 3, bit 2 to 5, type of graphics. This one we use, and we put it to 1 for ASCII. That's bits 2 to 5 of byte 3 of this byte. And that's it about this data. That's sang 0, sang 1, sang 2. So this one translates all this data and looks at that stuff, sorts which one goes here, which group of bytes goes here. That's each group is like one chunk, like for speaker it is frequency, duration, and type of data. For LCD that's color, type of graphical data. In our case we use ASCII all the time, and for ASCII that's oh sorry, it's not type of data. The type of data is programmed here, one of bits, and these are data itself, and that's is ASCII codes here. This audio, this graphics, and that's ASCII codes, 3 bytes here. That's it. So far we have sang 0. It goes to the it starts I think I'm not going to cover in details how I programmed GPU. We have characters. Here's ASCII programmed. Each character has its dots, its lines, pixels. And we have characters. We have a transpose map. This transpose function is needed because horizontal is vertical, vertical is horizontal. Here somehow differently made this stuff different than this. And here we have a whole screen. All the screen, line by line, is given here at the data, at the GPU data pins. That's 7 bits. As byte by byte, all the screen goes here with fixed resolution and there. But it goes from here to the interpreter, and that interpreter already knows the specific of this display, and you can find all the details. You can study, make a good study here at these codes of them. You will understand all this stuff. So far I will give a quick overview. We send all the screen from here, clocked by this, powered by this one. We send these bytes here, it gets them, and as soon as it received all this screen, it sends one by one all the bytes here, and all this data that it sent, this PPK resurrection, went from from here to here, clogged by this one, and it received them and some pins. You will find them in the which kind of pins are used. You will find, if you study the code, as you can see, we have port A, we have port B, port C, and so on. I have comments there, which ports are used for this. Here he have ports and which ports are connected to here. Here we have programming pins to program this one with that code. And also we have light emitting diodes. As a rule, my suggestion is, if possible, all the time use light emitting diodes for diagnostic purposes. If something goes wrong, something doesn't work at all, then you can change your code. Your code consists of steps, and after each step you can redirect the output to the light emitting diodes to find out what output of this step is present. And now so you can pinpoint, you can find the problem by searching step by step all this stuff that you put here, all the program. If that's a hardware faulty, you can see it. For example, the display is faulty. You can see that this one works perfectly. The last step of this program for him is all right. It shows nicely here. And when you send the diagnostics output of some step here, you can stop this by using exit command, and you will see here the output of this step. And about this display, I have this model of this display there, but I would like to say, if you use a contrast, if you don't use a contrast correctly, you won't see here nothing. You will think that this display is broken, defect, has defect. But in my case, I need to use a voltage divider. In description, in manual for this, you Google up for this screen, and you will find that instruction to use a divider. I don't use a divider, voltage divider. That must be a potentiometer. But instead of that, I use two resistors. One is 10, one is 10 kilo ohm. I don't use it. I don't see. One is 10 kilo ohm. Another one is 18. One is 10, another one is 18. And that combination shows the contrast that's pretty good. And why we use capacitor? I put here capacitor between plus and ground at the power. That's because if I don't use a capacitor, then this sound that goes out from here, it's dirty, and that's just because this screen makes the sound makes the current dirty. This screen somehow cheap make, and it doesn't, it spoils the current. And we have capacitor, the module of capacitors I've put there. That's 2000 microfarads. Do you remember microfarads? Drink. So sorry. So far we have received bytes here. We've transposed them by using function. They're transposed bytes for him. If we don't transpose, we can see here some stuff that's too vertical. So that's it. The keyboard, it's all the time being scanned by this controller. And that's it. That's let's take a look what we have here. Maybe I forgot something. Stage 2. It's 3D model. We have laptop version here. The power section we don't use here. Also this LVDS converter we don't use. That's there. And all the rest is the same, like here. And this diagnostics diodes I recommend, definitely. Yeah, that's the capacitor for the display power. That's clock for the CPU. This the same components, many of the same components that we use in section number 1. And these displays of this model, diodes, and this controller is at ATX Mega 256R3B. This one, and these three, this, and this all the same, this chip. Okay, and I hope you'll have successfully built this project for yourself, and what can be said, for the future. It can be upgraded. This way we can have different software. I'm using to build a software. I used yeah, Z80 simulator to write this in assembler. I've written this in assembler, then it helped me to convert this to machine code, and that's what I put here. And also for programming the memory chip, I used a controller. Yeah. I made such programmer. I made such programmer that's dedicated for the programming of these chips, read-only memory. You put one here, and you start it. That's for programming this controller, and you start it. Put the 4 volts here, 4.5, and it goes one by one, lights up the diagnostic diodes. In the end, you get erased and reprogrammed memory chip. And the code for programming you put here, the content of this one. Because by hand, to program all these 1,000 bytes, it's not practical. That's the meanings of codes of diodes. If that's successful, that's lit up. And that's it. Thanks for watching. And the future can be of this computer can be, for example, if you put here Pong game, and you can do the menu. If we start the computer, it doesn't sound like dun and doesn't put ready word, but instead of that, it can bring here a menu. You can choose like you want to Pong, the game Pong. You can have a virtual keyboard, virtual piano. You can have, for example, notepad. You can have a calculator, and that's all can be done in this hardware. In all this stuff that's present here, you can do this. I think it's all ready for the programming that way. And after that, you can find additional hardware that you can apply here. For example, for this computer, you can have radio communication, radio network with another computer like this. You can have a printer. The printer needs to be, if you connect printer, not directly here, but using, for example, such controller, you take out all the stuff from printer from inside, and you put here the controller, and that controls the laser That's a laser printer. That's control laser, and so on. That's just a quick overview what can be done next. So that's it. Thank you for watching, and all this stuff, all these modules, all these components you will find at the same folder like this video, and uh, you will have to search Google a lot. You will have to study a lot how it works, because it's not, for example, this GPU. I have only VHD code for, but this every hardware needs a programmer hardware, and this code can be different depending on the model of the GPU. I have put here the code that I have used for this specific board, but this logic is the same for all, and the pins we pull a different number of pin numbers pull a different, maybe different, but logic is the same. So that's it then. Thanks for watching, and bye bye.